Hello and welcome everyone. So today we'll again continue our discussion on Matplotlib, and we were in the types of plots in which we saw a lot of plots. And now today, before going to any plot, I'll introduce some of the concepts. I'll introduce some basic concepts of statistics. Okay, I won't cover them in detail, but I'll just give you a glance through them so that the material that we are going to cover in coming minutes you will be able to understand that. Okay, so these are the concepts from stats, and we'll see them in detail once we reach the statistics part, but here I'll just maybe cover them for the sake of completion. Okay, so the first concept that I'll cover is called as quartiles. Okay, what are these quartiles? So quartiles, basically they divide the data set into 4 equal parts. Okay, if you have a data set, so usually will have data set in machine learning, deep learning, where you'll be working with, or maybe you have any data. So this is a generic term, doesn't apply to machine learning only. It applies to anything that can be described as data, or it applies to any information. So but I'll talk about specifically in terms of machine learning and deep learning. So what these quartiles are, so if you have a data set, so let's suppose we can arrange the data set somehow. So now what these quartiles do is, these quartiles, they divide the data set into 4 equal parts, each containing the 25% of data. That's why they are called quartiles. Okay, quartile basically mean 1/4. And let's suppose we'll have like this. So we'll have a data. I'll make diagram like this. So this is our data. And based on certain conditions, we can maybe sort it, whatever we want to do. And then what we can do is we can say this is quartile 1. This is 25% of the data. Okay, and this is quartile 2nd. This is again 25% of data. This is quartile 3rd, 25% of the data, and rest quartile 4th. This is 25% of data. That's what these quartiles mean. So usually these are called as percentiles. So you might have heard about percentiles. 25th percentile. So this will be called as 25th percentile. And then again the 50th percentile. Then we have 75th percentile. Or in the scores also, when you see these scores of these competitive exams, they show you have got 99.9 percentile. They don't show percent, they show percentile. So basically they divide whole the student into these what are called quartiles. Okay, so usually we have this quartile Q1, Q2, Q3 and Q4, and each of them they divide the data set into 4 equal regions. Okay, then there is something called as interquartile range. Interquartile range, what that is the difference between Q3 minus Q1, difference between these quartiles. So this is called as interquartile range, IQR. All of these will be seen. So let me take an example. So let's suppose you have students. You have students in the class. I'll just take a simple example, and then you are taking an exam, and out of that exam they somehow got some marks out of, let's suppose, 100 or something. Out of 100 they had the marks, and now what you can do is, if you can arrange students in the increasing order of their marks, somebody would have got 30, somebody would have got 31, something like that, till like somebody got 95 is the highest score. So what you can do is, if you have, let's say, 100 students, for the sake of simplicity, you have 100 students. Okay, what you can do is, if you take the first 25th student, 25 student, so let's suppose quartile 1, the quartile 1, I can say a number, let's suppose quartile 1 is 52. So this means 52 marks is the quartile 1. That means the 25% of the students have got this 52. The first quartile students, they contain all the students which have got number less than or equal to 52 marks. Okay, the marks in first quartile are 52 or less than 52. Okay, that's one Q1 call will be given a number. The quartile 1 has 25% of the students which have got marks either less or equal to 52, and accordingly, let's suppose Q2, quartile 2nd, that's 50%. Let's suppose this is 60. That means 60 marks is the quartile 2. That means if you see 50% of the students now got the marks which are less than or equal to 50%, and this is usually also called as median. Again, accordingly you can see 75th quartile and quartile 4. Then now you can see that if you have Q3 let's suppose is 90. So you can say IQR interquartile range is 90 minus 52. This is interquartile range. Okay, all these things, they try to somehow summarize the data. Okay, all of these things are somewhat a summary of data. So because sometimes you don't want to look at all the data. If somebody gives you some numbers, maybe a couple of numbers, and from that you can somehow guess that data set will look like this. That's why somebody can give you, this is Q1, this is your Q2, and this is your Q3. From this you can come to interquartile range, and there will be other things. Let's suppose there will be, if you want to see central tendency, somebody will give you mean, and somebody can give you median and mode. So all of these try to summarize the data. You will have millions of data points. Now in order to give you a rough idea of what data is, so what you can do is, if you have this quartile Q2, Q1 and Q3, maybe Q4 also, and mean, median, mode, and maybe some variance also. Okay, variance. So these will be some numbers which will be summary of your data. Okay, what is the meaning of mean? So you know average. So just sum all the observations and divide by number of the observations. But there is a problem with the mean. So mean is basically susceptible if there is some outlier. So mean gets changed. Then people came up with median. They said, okay, median can't be changed by outliers. And then comes the mode. Mode is let's suppose the most frequent value that exists is there. Okay, and similarly you have this variance. Variance shows how much is the variability in the data. Okay, if you have a central tendency in the data, how much is data varying across. So all of these things that I'm speaking about, mean, median, mode, quartiles, variance, and they give you the summary of the data, because you can't see the whole data and you just want to get a glance of the data, how this data is. So that's why these things are called as statistics, because they are a static measure. So you measure a thing that's called as static. So these are these numbers, mean, median, mode, and these quartiles, these variance. Maybe there will be some other numbers which we will discuss in detail about in the probability and stats part of the course once we reach there. But I hope that you at least got some idea about what these numbers are. These numbers try to summarize data. Okay, and it can be the data can be about marks that people got in the exam. It can be about heights of people. It can be, let's suppose, income of the people. Data can be like that. It can be different types of flowers, maybe length of flowers, something like that. So there you can compute mean, median, mode, you can compute these quartiles, and you can compute the variance. Okay, these are the things will summarize it. You will have a rough idea about the data. Okay, and from this you will be able to compute outliers also. So outliers basically is if they don't somehow fit into these things which I am saying. Let's suppose most of the data will fall into this mean or median. Okay, most of the data should lie there. Variance should be this much. If there is a point which is very extreme, then you can say this point is an outlier. Okay, so in order to now we have these graphs also. So we have the graphs which summarize this data somehow. Okay, they summarize this data into graphs. Now instead of giving you all these numbers, if I can give you a small graph or something, if I can give you a small plot which can somehow make this data more readable, I don't need to give you this is the mean, this is the median, this is the mode, this is quartile, this is variance, this is that. So it will become a little bit hectic in order to write all the numbers. So it is better if we could have a visualization. So there is a plot known as box plot. Okay, this is the plot. So I'll just show you the plot first, and maybe after that, so this plot will somehow look like this. So we'll have something like this, something also called as box and whisker plot. Box whisker plot. So I told you what this shows. This plot will basically tell you the summary of the data. So if you have a data set, it will tell you the summary. So the function that we'll use in Matplotlib is called as box plot. So box plot, and then it takes the argument x. So this box plot, as I told you, is also called a whisker plot or box whisker plot. Okay, so it basically shows the distribution of the data. So all these things which I talked about, their summary, they somehow show you the distribution of the data. So it highlights the first thing, central tendency, maybe mean, median, or mode. It shows that, and then it shows the variability, that is variance maybe, and then it shows potential outliers, what outliers can be there in the data, and it also shows interquartile range. Okay, IQR, this Q1, the range between Q1 and Q3. Okay, and so how this will look like? This will look like this. So let me make it a bit neater. Maybe for most of you, this graph you might have seen for the first time. This will be something like this. You can see there is a box, and there are these whiskers. That's why it's called box plot or whisker plot or box whisker plot. So now what this box will represent is, this box will represent interquartile range. So this box, this range, the length of that box is IQR. Okay, this is interquartile range, and let's suppose consider this as Q1 and consider this as Q3. It depends on the implementation, what is Q1 and what is Q3, and there will be a central line like this. Okay, there will be a central line. This thing over here will be called as central tendency. So this can be median, mode, or mean, depending on how this has been implemented. Central tendency. Okay, and these things are, this is the minimum value usually. Okay, but it varies, and this is the maximum value. So you can see in between, let's suppose in between this, if data is summarized like this, so you have this Q1, now you have Q3 also, that gives you interquartile range, this gives you central tendency, this is the maximum, maybe the max value that you saw, and this is the mean value that you saw. Okay, this is what the data will look like, the plot will look like. Let's plot that. Let's now plot this, and why it is useful. It is useful everywhere. So many of the times, if you have this data, you'll just plot this so as to get to know, okay, this has so much variability, and all of this will tell you variability, variance of data. So how much is data varied? If this box plot, let's suppose, is too much lengthy, and you can say, oh, there is a lot of variability, you can compare the classes. You can see if this class has this much of length in the box fiscal plot, and other class has a much bigger box fiscal plot, that you can say there is a more variance, there is more variety of data. The data is quite variable. So applications I won't tell you, because most of the things, when you will see the data, and the first plot that probably you are going to plot is this. Okay, I'll start with whatever we saw, the test scores. We'll plot them. Let's suppose we have class A, class B, and class C. So what we'll do is, in all these classes we'll see the student will randomly generate some marks, let's suppose, between some things, and then we'll see we'll generate some 100 students like that, and then we'll plot it like that. Okay, let me go to the code window, give me a second or so. As I said, that there is this function known as box plot where you can plot this. So now let's start with the example of class score. As I said, we have three classes, class A, class B, and class C, and then the first thing that we'll do is import our libraries, import Matplotlib and this NumPy, so that we can generate data. So let's suppose we'll generate data for the first class. We'll have mean of 75 and standard deviation of 10. And for the second class we'll have mean of 80 and standard deviation of 15. For the third class we'll have mean of 70 and standard deviation of 20. This is how we can do it. You have seen how to use NumPy as a random module. So np.c, this is just for the reproducibility, and then we have test scores class A, test score class B, and class C. Okay, and this is what I'm saying, mean of 75, and give me such 100 points. In all the classes I'm saying give me 100 points. Now I'll combine this data. Okay, now you know how to combine the data. If you have data, you can just concatenate them together in a list like this. Okay, all of these are NumPy arrays. So this is my data now. Now I want to plot this. So what I'll do is, I'll say plot, give me a figure. I'll use a pie plot style. So till here I should run it. It should not give me any surprises. Good. And now what I'll do is, I'll say for creating a box plot, for everything we must create a figure first. So that's what I'm doing here. plt.figure. I'm using the pie plot approach. There's another approach which we call it object oriented approach, where we just collect this figure and axis, and we call basically a class. So here this is the figure, and then now if I have to plot this box plot, so how I can do it, I can say plt dot, and then I'll say box plot. You can see it in the box plot. Now the box plot takes argument. The first thing is data. I'll give the data that I have here, and then I'll see, usually they take other arguments at patch arts is equal to, you can learn about all these things in documentation. And then I'll say labels. I'll give it is labels, labels. I'm parallelly seeing the documents that I don't get it wrong. And this is class A label, and then for second I'll say class B, and then for other I'll say class C. These are my labels. Then what I can say is, I can say what should be the color and all of these things. So there is some it's a dictionary sort of thing. So what I can do is, you can see this box props over here somewhere. So box props here, so you can give it a dictionary. So where you can mention that face color should be this, color of that should be this, and you can also see median props, whisker props, and you can basically manipulate all the things that there are in the box whisker plot. There are arguments for that. So box, you can give it a dictionary. As I said, it will take dictionary, and then what you can do is you can give it face color. Okay, rather than typing all of this, I'll just copy it from the documentation here. What are the arguments that it takes, so that I don't make mistakes while typing. Okay, so this is the box prop. So what are the properties of box? This basically means box properties. So there is a box, there are whiskers. So these are the box properties. For box, give the face color light blue, and in general color as black. And then there are median properties. Median is that median line. There will be median line also there. So median line, give the properties of that also. So the properties for that is median properties dictionary. I'm just giving color. You can specify other properties that you can check in the documentation. Again, the same thing. I'll just for the other, and then we have whisker also. So for the whiskers, I'll also define whisker properties. Oops, this gave me the plot because without giving more things, I just ran it, and it just ran the data and took the default values. Let me just add some properties so that it looks, and whisker I have given. And again, for the caps, the end things are cap, I'll just give them black. You can just change the color, and these are all properties, and you can see it from the documentation. And then I'll give flyer props, and this is markers. Okay, these are all properties for different things that are there in the whisker. Okay, so I have given box plot, the data, and the pie artist, and this was enough. And for all these things there will be default values, but I just wanted to show them. I just wanted to show you that it takes all these arguments. If you can see it over here, okay, there are a lot of things that it takes. Okay, auto range, manage text, whisker properties, cap properties, mean. Okay, and the plot will look like this. Okay, so from this class A, you can see that this is the median. Okay, the score, minimum score is somewhere around 45 or something, whatever it is. The maximum score is around 90. Okay, and then you can see it over here also. So it is just random. So these are the outlier thing, and these are whiskers or thing, and this is median. Okay, you can see the variability in class B and class C is a little more than class A, and you can see all these stats just in one glance. Okay, nobody needs to tell you and write down the stats, so you can just see it over here. And again, you can just put these title, and you can put the labels, X label, Y label. That should be the custom by now. So if you want to put them, so you can put it like this. Give the title, give the X label, give the Y label, and should say the grid. And for the grid also give the alpha score, that's basically transparency, and plt.show. This is how it will look like. Okay, I hope this plot is clear to everyone now. Okay, let's move on to the next plot. This was the plot which we call as box plot or whisker plot or box whisker plot. There is another plot called as error plot, error bar plot. This is what it's called. So again, if you see the function that I'll just call over the function first. The function is known as error bar. This is the function, how Matplotlib defines it. So an error bar basically is a graphical representation that displays the variability, uncertainty. Okay, uncertain data points. Error can be represented by the uncertainty in the measurement. Let's suppose I'll have some data point like here. I measured the two coordinates. Let's suppose there are two measurements. So this is temperature and this is, let's suppose, pressure, something like this. Something I'm just making two measurements, temperature and pressure. So this is what I predicted. I said temperature is like this, okay, and pressure is like this. So this is the pressure value and this is the temperature value. But what will happen is there will be some deviation. So I want that error can be in this range, okay, and for this pressure error can be in this range. So you will see a graph like this. You will see for this point, so error of margin will be like some graph. You can look it like this. Okay, this is the error, the uncertainty basically. So in the y-axis, this much is the error, and the x-axis this much is the error. So you can just visualize these things. So the error size basically will, the length of that error will indicate the degree of uncertainty, how much uncertain is the value. Even if you have good equipment, but still there is a chances that you will get some error. So it is better to show the uncertainty. Okay, the measurement, actual measurement is this, but with this much of error, with this much of uncertainty. Okay, because in many real world case scenarios, what will happen is you will measure something, but you will measure it with some uncertainty. That's why to show this graph, and these are the actual, you can show this is the data point, but this is the uncertainty in my pressure, and this much is the uncertainty in my temperature. So you can show the graph like this. So again, what you can do, again, this can be used in scientific research and quality control, environmental studies, market research, because everywhere where you see some uncertainties involved in the data. So you can show that I have this data, but this is with some uncertainty. So you can also show it by using these plots, which are known as error plots or error bar plot. So now how to make this error bar plot? There is the function which I showed you. Let's first go to the code and maybe simulate one of the conditions, one of the case studies rather. So again, the same thing, what I can do is I can create something like this. So if you see, oops, not copying at all. So this is the seed. I'm just creating sample data, x values, give me some 10 values between this. So y values are some sign for the, this is just for the demonstration, and then I'll create the error plot. Okay, this is the error, and now again I'll use the same pie plot style. Okay, this is the figure, and I'm saying x and y. So I should also say x, y errors. So I should also give how much errors are there. I should also simulate errors. So before this, I should be having error values. These are my errors. Let's suppose my error comes from some uniform distribution, and these are the errors from 0.1 to 0.3. There are some errors in y, and there are some errors in x. So I have these x values, and I have these y values, and these are the y errors and x errors. So I'm giving x and y with this error. Okay, you know about this FMT color, everything. And these are the labels with there, and then I'll just customize the plot and write the title, x labels and things like that. But the important function is this error. It takes the x value, it takes y value, and then it takes how much is the error, how much is the error in the y, and how much is the error in the x. And you will see the graph that I just made on the tab. And if I just print it, you can see something like this. This is the measurement, okay, but with y you have this much error, and with x you have this much error. You can see these error regions. So usually this is quite useful when you are dealing with real data, because there whenever you measure something, you will measure it with some uncertainty, with some error. So it is better to tell, okay, this much error is expected from the data. Okay, and if the error is more, then you might take a decision: should I use this data for my research work, or should I use this data for this? So you will make a right decision if you know how much error uncertainty is in the data. So it will be better. So here we have a plot which is known as error bar plot. Okay. Before going to other plots, so I just again need to show you some concepts so that you have the basics, and then we can move to the other plot. So I'm moving quite fast in these plots because there is nothing much to learn. They are just the simple graphs. I think you can. Yes, you have questions? Go ahead. There is something called as KDE, kernel density estimation. We'll see all these things in detail once we go to probability stats, and then how to do this KDA, what are the things that we do. But I think you have this background that you know how to plot histograms. Okay, so histograms basically show the distribution. So these histograms were like this. They were somewhat like this. Let me make a normal distribution histogram, something like this. Pretty bad at drawing, but I think this. Now what you can do is, if you keep on decreasing the size of bins, okay, so what will you do is you want to smoothen this out. If you want to smooth curve, because when you plotted histogram for the distributions, so that function basically is called PDF or PMF. Okay, if you see a function like this, so this function is called as PDF or PMF, depending on what type of data we have. We have seen that we can draw histograms for the discrete data or for the continuous data. If it is the discrete data, we call them PMF, probability mass function. If it is a continuous variable, let's suppose the height of people, that was continuous. In discrete, we had this dice rolling. So that time we'll call it a PDF, probability density function. So that this function will be that, because you can see this curve is actually a function. But now, in order to make it a smooth function, we need to do something. That's we do this kernel density estimation. Okay, so what do kernel density estimation does is, so it basically is a non-parametric method to establish this probability density function. So it tries to estimate these probability density functions. I won't go in much detail because I won't assume any probability background right away. But here, if you want to plot this PDF from these histograms and you want a smoothed version of this, so I said this is a non-parametric approach. I'll tell you what non-parametric means when we go to the probability. And this KDA is basically, it produces the smooth curve. So you will have this sort of histogram, and you will apply KDA on this, which basically what it does, it usually is this kernel is usually a Gaussian function. We'll see what Gaussian function means to establish all these smoothness into the curve, and you can just fit maybe a distribution and you can come up with this PDF. And PDF has a lot of applications. People who know probability, they know how much PDF is important. Okay, so I'll just draw something. So this is how usually this will look like. But I'll use Seaborn here. So Seaborn is just an extension to the Matplotlib. It's a wrapper around Matplotlib. So in the code, if you can see, so I just imported Seaborn as SNS. So I'll say figure and KDE plot. So there is a KDE plot. I should maybe have scores or something. I should maybe, do I have scores? Scores is not defined. But yeah, I can plot it, but I need a lot of plots, so we'll see. So even I don't have Seaborn installed here. I should maybe do an installation. Give me a second. So now if you see here, what I did is I just have the scores which are just normally distributed, and I have this is the mean and this is the standard deviation, and these are 1000 points, some 1000 scores. So I am calling a function which is called as KDE plot. So you will see it's a smoothed out version of histogram. If I just print it, you can see it like this. Okay, so if you can fill it just like histograms, you can have this histogram, and I somehow smoothed out it. Okay, so this is how I smoothed out. Maybe I can also plot on the same. I can say PLT dot hist, and then I'll give the scores. Okay, if you can see, this is the histogram. Okay, so this is the histogram. So I have just by taken everything as default value. So if you now want a smoothed out version of this, so what I can do is I can just do it like this. So this is the smoothed out version of that. Okay, that's by using the kernel density estimation, and we'll see the approach, basically how it is smoothed out. And there are a lot of methods by which we can do smooth out, and kernel density estimation is one of the methods. So this over here is can be thought as a probability distribution function of a continuous variable. If you can see x, these scores are continuous, so they contain continuous range of values. And now what we have done is we have a smoothed out curve from the histograms by the help of kernel density estimation. Okay, now I'll come to the important plot, that is Voilin plot, which we had a question about. Give me a second, so I should turn this code window off. Okay, this I actually showed you for the next plot, that is called as Voilin plot. Voilin plot. Okay, so what this Voilin plot is, this Voilin plot is a hybrid visualization. Okay, it combines the elements on box plot, whatever we had in the box plot, and the kernel density plot. Okay, we have this KD plot, you saw that KD plot, kernel density plot, and then we had box plot. So this Voilin plot is somehow hybrid of that. It combines the elements from box plot as well as the KD plot. So it provides detailed representation of the distribution of the data of different categories, showcasing not only the central tendency and variability, but also show the density of the points. Because what this KD does, or what this histogram, what do they do? So these KD plots or the histograms, they show you the distribution and show you the actual how this density of the different points look like. And now this box plot basically showed you variability, central tendency, and all of these things. So if you sort of combine these together, you will get this what's called as Voilin plot. So it, because why it look like a violin, it looks like this, it looks like a violin. That's why it's called Voilin plot. It looks somewhat like violin. Okay, and then we have in between we'll have box. So I'll just show you. Maybe we'll again draw the same plot for the classes that we had earlier done. We have class ABC, and then we'll draw a Voilin plot. So what is the function there? The function that we'll use is Voilin plot. Voilin plot, and then we'll give this data. Let's go to the code window to directly show it there. I hope that you got the clarity of what Voilin plot does. So I'll just copy the same code that we had earlier. Just wait for the questions if you have any. So you see this class A, class B, the same thing that we had, and now we'll again combine the data as we did earlier. Okay, now what we can do is we can plot this Voilin plot. So we'll just plot the figure. So I just want to confirm it is right. Yes, it is, giving no errors. So this is my plt.figure size is this, and then I can say this is the Voilin plot. I'll say plt.Voilin plots, and then I'll say show me the means and show the medians also. Okay, so this takes a lot of arguments. If you can see it, width, show means, show medians, quartiles, points, and whatever you want to see, you can show it over here. Okay, and then I'll just customize the plot by adding the title, by adding these classes, and by adding the labels. If I now draw this, so you can see this is the Voilin plot. Okay, now if you see this is sort of a box and whisker. So this over here looks like a box and whisker. Okay, this part. And if you see these sort of things, so these look like our PDFs. Okay, our probability density functions, or what we can call KD plots. So these things look like KD plots. If you just flip it, this is like the straight. If you just flip it like this or this, so these things are symmetrical. So whatever you see here, you see the same information over here, and then you see these whiskers also. You see this box in between. Okay, these are the median lines, and you can see this shows the variability also. So it combines both the things. It combines this KD plots or probability density functions as well as the box whisker plots. Okay, that you can clearly see over here. So this is again, if you see this is a symmetric plot. So here all of this is a PDF or KD plot. So in between we have a box and whisker plot. So it combines the features of the box whisker plot. It showed you variability data, it showed you the median and tendency, it also showed you what are the min and max values, but it did not show the density, how are the point distributed, how are the different data points distributed. But here you can see that this also does that, because it also shows you what is known as a KD plot or a probability density function. Okay, this is about the Voilin plot. And then there are event plots also. I won't cover that because many of the times you won't use the event plot, but there are different plots. There are at least hundreds of these plots, but I am just covering the important ones. Okay, so let's now move to the I think we have 2D histograms also. You should be also knowing 2D histograms. That's also good. So let's move ahead and see what these 2D histograms are. Because you saw histograms were just, we had something and then we had the value of that, we just check the maybe frequency or some distribution. But what if we have let's suppose height versus weight. Okay, we had something like, we had two variables and we want a third thing to observe from that. Okay, if we have to do something like that, so for that we have 2D histograms. Let us just hide this. So we have 2D histograms. Okay, so what this 2D histogram basically does is, so 2D is this again a graphical representation that captures the joint distribution. So this basically captures the joint distribution. So we'll again see what this joint distribution is. People who know about probability will know what joint distribution is. So usually if you see in histogram, so there we had a variable, so we had this and we're capturing a probability distribution. Let's suppose these were marks. Okay, we're saying we want to capture the probability distribution of this variable marks, probability distribution of this marks. Now let's suppose if you have two variables, you have let's suppose marks and some other thing, height and weight, and you want the joint probability of, let's suppose, these variables x, y. This is called a joint probability. Okay, what's the probability of this and that happening together? So they should happen at the same time or simultaneously. So we'll again see what the joint distribution is, but here you see that now we are not just finding distribution of one variable, we have distribution of two variables. Okay, and that's why it's called joint distribution, because we have, and then this allows us to visualize the relationship between these two, and it reveals correlations, then say estimations and all of this stuff. And how to do that? I'll just have this weight and height, and we'll have joint distribution of this. There are basically two ways to plot them. The one is called as, I think, there are hexagonal packets also, hexagonal these cells. So this is one way. Okay, this is height in centimeters and weight in centimeter, and these are number of individuals. So basically I want to see height and weight, so and how many individuals are there. Now if you saw initially what we did is we said height and the number of individuals. Now we have two things, we have height and weight. Now each of this is called as a color bar on the right side. If you see, this is called a color bar. Oops, can't see it. So this will look like something like this. So what there is, we have this height and we have this weight, and here we have this number of individuals. The more colored it is, so you can see this color bar on the right side. So 0 basically means there is no individual with this height and this weight, but the more you go, you can see the central thing. You can see these at 12. So these are this is the weight and this is the height. So how to plot this? What I just did is I just created some height with normal distribution, and I created some weight. Okay, and I said figure and histogram 2D, and now I have to give two variables, height as well as weight, and the number of bins. And then I gave the C map as color map, how much color, and there are a lot of these. I gave blues. There is, I think, Verdis also, which I usually use. VRIDIS, I think spelling is wrong. Okay, this is the, and there are a lot of color maps. You can see it. I hope yes. So you can see this is in the color map. This is usually what I use when I have to plot these things. So now you can clearly see in the first histogram you just had one distribution. You had a probability distribution with respect to one variable. Now if you want to have probability distribution with two variable, which is called a joint distribution, so you can just use this plot 2D. Okay, plot 2D, and then you have height and weight, and you can see this color basically represents accordingly the number of individuals. Okay, 0 basically means this, you have nobody which has 140 centimeter height, and the weight, let's suppose, is some 20 or something. You have no, and most of the individuals, if you see, fall into these categories. Okay, this is 0, this is 2. Many of the individuals following this, you can see this 12 and something. You can interpret the graph accordingly. And there is one more way to visualize this 2D by using the what's called hex bin. Now you see these bins are rectangular or maybe square shape, but what if you want much space? Okay, so what you can do there is you can just say this hex bin instead of histogram 2D. You can say hex bin. Okay, and the same graph, but this looks too cluttered. Okay, let us do it in a better position. Yes, so you can see now this looks quite neat. I have just did this. So I said these are my this is my data, and this is the figure, and this is hex bin. So these are basically 2D plots. So these are 2D histograms. Okay, one is hex bin, the bin basically is hex, and histogram 2D basically is you have the square thing over here rather than this. I hope these plots are clear. Now I'll go to one of the important plots that you have, most of you might have seen, that's called as pie chart. Okay, so how does Matplotlib give you the ability to create pie charts? Pie charts. So pie chart basically, there is a function directly PIE. This is a function which takes some values. So pie chart is a circular statistical graphic that divides the thing into slices. Like, let's suppose if you have a data which is categorical data. So and then let's suppose we have 5 categories, and we want to see how much of the share is with each category. We plot something like this. We say this is a circle which has, let's suppose, all the 100% of the property, and let's say we have these categories, something like this. Okay, we have these pies. Okay, and then we'll create categories. So each slice basically is of the size which is basically in terms of this proportionality. This we have categorical data, and the categorical data, what we want to do is you want to give the area of the slice that should be somehow correlating with a proportion, how much proportion each slice has. Okay, and the graph over here is pi. Why does it use? Business reports. You might have seen business reports all the time. And they show, okay, companies use this for presentation to show market distribution among competitors. Okay, this is our company, this is company A, company C, and this is how much market has been captured by different competitors. And in survey results, in research, pie charts, they're usually used to show the survey results, such as participant demographics or the preferences, so that as to make it easy for the communication. And again, the budget allocation, if you want to allocate budget in the teams, you say, okay, this much of budget is allocated team A, team B, team C, something like that. And social media analytics also, so marketers can utilize the pie charts to represent and break down the engagements across different platforms. Okay, and it will help them to focus the effort in a particular way, so that because they have the visualization of how it's distributed. Now let's do one thing. Let's create one pie plot where let's suppose we are the retail store owners. We have some store in which we have electronics product, we have clothing, we have home and kitchen, we have books and other things, and we want to show when we were basically selling those things. So what is the distribution of our sales? Okay, sales data that let's suppose we have. So in that I'll create a pie chart, and pie chart can be I think this can be more useful because there are so many flavors how you can create this pie chart. I'll start with a simple example. Again, the Matplotlib that is included, so I'll write categories. So I have category, let's suppose I am owning a store, and I'll have category, maybe categories. Okay, I'll say, let's suppose category electronics, clothing, and home and kitchen and books. These are the categories I have written over here. Okay, this is electronics, clothes, home and kitchen, books, and others. Then I have my sales data. Okay, I have my sales data like this. So this is 35% share, 25% share, 20% share, 15 and 5. This is percentage wise share. Okay, I could have just computed the percentage also. If I have sales data, from that I could have computed this sales percentage. Now the simple thing that we have to do is create the figure that we have been creating since day one. The plt.figure, figure size is this much, and then I have to create this plt.py. Okay, so this is the figure that I'll create. Oops. Okay, plt.py, I'm giving sales data, I'm seeing labels in the categories. Okay, and this is the formatting, how do I want to format it, and then this is the start angle, what should be the angle, and color points, all of these things. There are a lot of these parameters which you can read about in the documentation. If you go forward this pie, it should show it. You can see how much things are there, and you can read about each of the arguments, and it's practically impossible for all the functions to remember these. So the best resort is documentation. Go to the documentation and see it. I want to customize this plot, and by customization I mean just add these titles and things like that. So this is actually this axis is equal, basically ensures that aspect ratio ensure pie chart is circular. It does not go that maybe something like ellipse or something. Now you can see this. These are the books, these are other, this is my retail store, and it is showing the percentage wise distribution, and you can see over here this auto PCT is how is it showing these numbers in here. Okay, this is the simplest plot. And let's now see what is called as exploded pie chart. By that explode you mean you just want to take one slice out, and you want to focus on one slice. You have this whole thing, but in the presentation sometimes you might want to take one of the slices out. So for that what you can do is you can just add one more argument, that's called explode. If you see this, so here I have these labels, these categories, I have the sizes, maybe the percentage share, and this is explode. Explode is some sort of list. Explode, the first slice basically means write everything 0 0 0, and I have just added 0.1. So if I wrote 0 in here also, it won't explode. You will see this chart is like this. Now if I want to explode, how many things are there? A, B, C, there 4 things are there. So if I want to explode one slice, so what I can do is I can say explode 0.1, or maybe and then it'll bring it out. It'll bring this A slice out. Okay, by this factor 0.1. So 0.2 basically should get it a bit more out. You can see this. I think 0.1 looks much better, so that's what documentation mentions, 0.1. So you can see I have seen axis, sizes, everything remains same. I have just added this explode. Okay, explode basically just take it out. Then we can do one more thing. We can add shades. Okay, they are called as shaded pie charts. So in shades, what you write is you just write shadow is equal true. So you write shadow is equal true. So it will give it shadow. You can see this shade over here. Okay, it makes it look like 3D. Okay, and then what you can do is you can also say if you want a circular thing, donut shaped pie charts also there. If you want a donut shaped pie chart, so again the same thing is you just have to add central circle there. Okay, you have to add central circle. So I'll show you that. But usually your job will be done, but I'll additionally show this also a functionality that's mentioned there. So what you did is pie chart, size, labels, and this is everything that you saw. But here now what we did is we said center circle is this. So we saw center circle is this, then we added these things so as to get a donut shape pie chart. This is the donut shaped pie chart. Sometimes you might have seen charts like this also. This is CBA, something like this. Okay, and you just wanted to add the circle. Okay, in the circle also this is also how we can draw circle. Okay, circle is the XY, and this is the how much radius do you want. If you want a little bit smaller, so you can just add this. Okay, this will become a little smaller circle. Okay, and you can read the documentation. And I myself have not remembered all the argument that this take, but the good point is that we have extra document, we can directly go there. And I think FC white basically means what should be the color of the circle. If I just add black, it should add black over here. You can see this is the black added. But important thing is you have to add it to the figure plt.gcf. Okay, GCF I think get the current figure, so you can read it. You can read all the documentation, whatever it is. Okay, then plt.gcf add this artist what is known as center circle. So you must know the syntax how to do it. Okay, and if you forget it, resort to the documentation. Go there and you will find plenty of examples there. Okay, this is about the pie chart. So you can create a couple of pie charts together also. So however we were doing it, maybe if you want to create pie charts back to back, and you can do that, because that's only the functionality how we used to do it with the other figures that you can do with the pie chart also. Okay, one more plot I'll show is something called as empirical CDF. So many of the times we'll plot CDFs. Okay, so how CDF looks like? So it is we have PDF and then we have CDF cumulative. I should explain it a bit so that we'll use it in probability. I'm only covering those things which most of the times we'll use in our probability or stats lectures. So we have something called as CDF. Okay, so you saw PDF somehow looks like this. It looks like this. Okay, so what if you can cumulate this thing? What if you can just keep on adding these things? So if you convert this CDF, this is PDF, sorry, this is our PDF, probability density function. So if you can convert this into what is called as cumulative density function, that means right now if I take this value, so I'll take, okay, with this value, let's suppose x, what is the probability that x takes this value, something like this. Okay, so you can just plot maybe a probability or whatever frequency. So if you want to convert into CDF, so what we can do is we say we'll keep on adding all the things till here. Okay, all the things will be basically added till here. So we'll have a plot like this, something like this. But this is always increasing plot. Okay, we'll have CDF. This is our PDF. This will be our CDF. So this is the probability distribution function, but this is showing the distribution. This is again showing distribution, but it's showing cumulative distribution. This was showing individual distribution as in histograms. Okay, if I talk about histograms, so histograms will look like this. So you have one histogram, and then you have second, you have the third like this, these bars. But what if you want to add them together? Now you will add this and this so as to get. So initially it will start like this. So it will keep on growing, it will keep on growing. But because why? Because you are adding these things. Okay, so you're doing the cumulative add. So I don't want to go into details, otherwise we'll have to introduce random variables and the technical details of probability and these things. I just want to give you the glance that these are the graphs that Matplotlib has. So see, PDF is probability density function, it shows the density, and this is cumulative density function, it shows the cumulative density. I have explained what is the meaning of cumulative. So we have something called as empirical cumulative distribution function. Okay, so it will look something like this. So it will show it empirically, not the exact value, but it will show the things empirically. And we can use our line plots also for this, but we have a particular thing. So you can see over here, so I have sorted the ages. Okay, and I am doing this NP range. This is the y-axis that I have, and then I am seeing ECDF. Okay, CDF is cumulative density function. So we have not density, so distribution function. So if I just print it, so you can see it, something like this. I think we have a question over here. Yes, go ahead.
Yes, sir, now it is visible.
Yes, so I was showing you that this empirical cumulative distribution function. So I said, let's suppose you have this x, I have this age which I have randomly generated, and then I have also this y-axis, and then I can just use this function ECDF. empirical cumulative distribution function, which will be always increasing function if you see this, because it's showing you the cumulative thing, cumulative distribution. As I said, the difference between PDF and CDF will be clear once we go to the probability part, but here I just want to show you PDF somehow shows you the density, probability density. But what if you want to keep on adding these things? Okay, the probability less than this. Let's suppose if I say these are my x values. Yes, to make it a little bit clear, I am not satisfied that everybody got it. So this is my x value. So let's suppose this x value is 1, 2, 3, 4 and 5, something like that, and this bar is like this for the 2, for the 3, for 4, for 5, something like that. This is the graph. If I tell you, okay, give me a value, you can give me the frequency corresponding to it. Okay, but what I can do is, if I just smoothen it out, you will see a curve like this, you will see something like this. So this I'll call a PDF. This is probability density function. So what I can do now is, so if I keep on adding these, so here you will add this and this. So let's suppose you have at this point you will have this value. Okay, at this point you will keep on adding both of this. You will, let's suppose, get this value. So at this point you will add this and this, so you will get this value. So at let's suppose 0.4 you will add this and this, so you will get this value. At 5th you will add everything. So you will see that our PDF somehow looked like this. So this was our PDF, and our CDF will somewhat look like this. It will be continuously increasing function. But all these details will require to understand them thoroughly and see the technical details of this. We will need the background of probability and stats, mostly probability and random variables and how the distributions are. That's why I just wanted to give you intuition. Okay, so we have this PDF. It is constructed from histograms. So now what if we can cumulatively sum them continuously? So this value tells me, okay, what is the frequency at 0.3. So if I say in terms of CDF, okay, if I just give you at 0.3, it is not just 0.3, it will say less than equal to 0.3. Okay, what is, let's suppose, what is the chances, or what is the frequency that the x will take value less than equal to 3. So you will have to naturally add these things together. That's why you will see the CDF is an ever increasing function. It keeps on increasing. Okay, and you see this PDF, it shows you the probability density, and that's why here we showed the function that was empirical probability distribution, which is continuously increasing function. Okay, this was the distribution. So because we studied a lot of the graphs which are related to distribution, now we will move to some which we call as grid data. If we have grids of data, all of these concepts will be used. Please do watch these couple of times so that you know that these functionalities do exist in Matplotlib. And also for the refreshing, you should just see the syntax, and once you are at least comfortable with them, then you can use, because they are just tools. If you see it, I'm just adding more tools into your toolbox. You should know when to use which tool. Okay, and we have seen a lot of graphs. I haven't seen any online tutorial or anything covering it with such detail, all these graphs, but we'll be mostly using them in our mathematical illustrations, or maybe whenever we go to some machine learning model, we'll use them heavily. And most importantly, we'll use them in EDA, exploratory data analysis. That's the first stage if building any machine learning product or any project that you will be doing. The first part you'll have to analyze the data, and you will have to perform this what's called EDA, exploratory data analysis, and for that you must know what are the tools that are there. Okay, and these are the tools. So now we'll move to what's called as grid data. If you have data which is somehow in grids, and for that we also have a lot of graphs that can be plotted. So one grid example of the grid data would be image data. So images, they are somewhat like grids. Let me just clean this code. I'm saying that we will now focus on what is called as grid data. If we have data which is in the grid format, okay, and this represents information across different grid coordinates. Okay, it's often structured in either 2D or 3D. You might have let's suppose longitude, latitude, or maybe depth or something like that. Okay, this is called as grid data. So each point in the grid holds a value, and that corresponds to the specific measurement or observation, like temperature, rainfall, air quality, population density, and it can be a lot more than that. Okay, so why do we find the applications in terms of machine learning? The image processing is the most easy thing to understand, because if the data is grid data. So digital images are the prime example. Why? Because you see images are composed of pixels, then pixels are basically in 2D. Okay, and then we can also think if we have a depth in there. By depth I mean you have R, G and B. You have 3 channels of colors. You can see it as the data like this. So you have R, G and B, and this there are 3 grids of the data. Okay, and this is what a typical image is like. This is what an image will look like. Oops, not able to write. It went to YouTube, I don't know why. Okay, so you can see this is the image data. Here you will have an R channel, a red channel, a green channel and a blue channel. Okay, and then each of these channels will be a grid data, so there will be a bunch of pixels. Similarly, in the geographical information systems, we call it GIS, the data is often stored in gridded format, in which we have let's suppose population density estimation, we can have terrain modeling, we can have raster data and a lot of things. And even in the climate, if you see weather forecasting, there you have these weather model which represents temperature, precipitation, wind velocity, and all, and different these things are shown in grids. And in the medical imaging, as images are the part, and in the medical image, in the 3D graphics modeling, in NLP, natural language processing, we also show the things in grids, because we have these vector embeddings. So you will see something like this there, which I think we have covered this as data matrix. So if you have word 1, this will be word 1, this will be word 2, this will be word 3, a grid of data will be there, something like this. Okay, now there are different plots or different graphs which are used. The first and important graph is image show, IMSHOW, an image. This basically shows an image. So this is one of the functionality that Matplotlib gives. So this function, it is used to display an image, or maybe where we have certain value. Let's suppose you have a certain value, you have a grid of values and you want to show those values, so you can use this image show. Okay, and each of the values will correspond to a pixel or something. Okay, and then you can also represent color graphs. Let me again show it by giving example. I'll just generate some x and y and z values. So what I can do is, and I'll just show you the image. Let us go to the graph. So here is the code. So if you see this, so I'll import this and generate some random samples, and this is my x and y, this is my mesh grid with these values, and then I'm showing this is my z value. So z value is sum of this np.exponent of minus x square plus y square. This is a function which is taking x. So if you see this function over here, so this function over here is just exponent of, so you just take an exponent of minus x square plus y square. This is the function that I just want to see. Okay, and now if you can see the function over here that I have used is IMShow. So image show basically is this z. Okay, this z value. So this is a particular value which is computed based on this x and y. So I have computed this x and y, then I have created an exponential function that's taking exponent of minus x square plus y square. So this is my z data. So if I want to show you the z data, so I should be able to show it like this. These are the values. If you see, this is like our grid data. Okay, now what I can do is I want to plot it. Oops, I want to plot it, so I can show image show because z will have certain values. So I'll show this z, and then you can go to the documentation to learn about all the things that it takes: interpolation, alpha, vmin, vmax, origin, extent, and all of these things. Okay, then origin is lower, c map is the color map that I'll use, and the color bar is that right side color bar which you put. Okay, that this is what intensity shows. It shows the Gaussian intensity distribution. Okay, because that the function that I use is Gaussian function basically. So here it shows the intensity. So intensity varies from 0 to 0.8, and then you see the most intensity is around here. Okay, the x value is this and the y value is this, and you can also print the image with this. Okay, let's suppose I'll just print an image. You can read the image just as a pixel value. So here in the sklearn it should be there, but I don't think it is there. Let's see if it is there. But yeah, it is not there. Give me a second. So if you see this, so here what I have done is I have just created a sample image. So image data is, let's suppose, np.linspa. I have created this, and I am creating a grid of this 10 by 10 grid. Okay, because I am creating 100 values. Okay, with this 0 to 1 in this particular range, and I am creating 100 such values. Now I am reshaping it into 10 cross 10 grid. So this is like image. So I'm just having a sample image. Let's suppose some images like this, which is of shape 10 by 10, and then I'm asking this image show to draw that. Okay, and C map is gray. So by the gray, it will show that color bar. So it will show that C map into gray, and we have this color bar also which shows pixel intensity. If you go this, and now you can see this because value will start from 0.1, 0.2 till 1. Okay, so these will be 100 values. So that's why you can see it first starts with dark, and that's 0 values, and then it goes to the extreme light value, that's 1. Okay, because we have created the values in such a way, because this linspace, it will create values in like this 0, and then we have to create in between 0 to 1 we have to create 100 values which are equally spaced. Okay, and then I am reshaping it into 10 by 10. If you see, it's a grid of 10 by 10. So the first row of the grid will be the most darker, and once you move ahead, and at the end it will be lighter. Let's consider this is an image. So if you have image data, you can just say you can say plot that I am show, and then give the image data, and then you can also mention that CMap. So CMap over here is gray, and then you can show the color bar also. And similarly, one more thing where you will use them is sometimes for what's called as confusion matrix. Okay, confusion matrix I won't discuss here because we will discuss it in the matrix portion of the machine learning deep learning. So confusion matrix shows how much things did you got right, and then from the confusion matrix you compute different metrics like F1 score, recall, precision, and all of these things. Okay, I hope that at least you got the clarity on this IMG show, and I have some image over here which I would like to show. Okay, so this is our we have correlation matrices also. Okay, where we compute the correlation. We have this image data which I just showed you. We have the temperature data also, which let's suppose is a Gaussian data, and then you can see it. I'll have 3 plots. This is my grayscale image, and this is my heat map of correlation matrix. Correlation matrix is how the data is correlated, how the features are correlated. Consider that in each of these things we will have a variable. Okay, in each of these things we'll have a variable like this. This will be x1, x2, x3, something like this till xn. And similarly we'll have here x1 till xn, and we want to see what is the correlation between these. Okay, by correlation I mean if it is more stronger correlation, that means the value will be much red or something like that. And here in the last graph, if you see it, in this last we are somehow showing the similar temperature distribution. How is the temperature at a different place? Let's suppose this is the latitude, longitude, and what are the hot. You might have seen these heat maps also. Okay, in heat map you can create the heat map like this. So in this example I have given some latitude. So here this is the longitude, latitude, and then I have created this color bar over here and shown how much which place is basically much hotter. You can do it by using these IMH show. And just going over the code to show you that it's not much difficult. The same thing is you are plotting this, so you should be experts by now. Okay, this is my image data and printing the image data. I showed you this, and again the same thing here. I want to just draw a correlation matrix of 10 by 10 numbers, and then again show this CMap is this, and then all the things you know. And here I'm just having the distribute. This is my x and y. Okay, this is my latitude and longitude. Okay, let's suppose temperature somehow follows this equation. Somehow, otherwise temperature usually will not follow this equation. I'm just showing you for the demonstration purpose. And then you can say heat map. This heat map is there, and I say x2 is equal to image, and give all of these values, and then we can just show this. Create color bar for the heat map, and then orientation is vertical, and all these things that I have mentioned over here. Okay, who feels now they can create these things? Okay, I want your opinion on this. Am I going too fast? The question is, whatever these graphs are they basically shown in 3D, but we are somewhat trying to draw them in 2D? Okay, that's a very valid question and very genuine question. Okay, let's see it like this. You have one variable. Okay, you have one thing, and that varies and it gives a result. So that basically demands that you should give me the things in 2D. So as in, let's suppose you have height of people, and you want to check the frequency. How many people have this height? Now you see this variable there. If you see, this is my independent variable. So you have one independent variable, and then we have one dependent variable. Let's call this x, let's call this y. So y is the count of people, and x is the height. So based on this height you are getting the count. That's why I am calling this variable as independent variable, and this thing is dependent because its value depends on what is the independent variable. And now you can see that we have two variables in the picture now. So in order to show a thing in if we have two variables, in order to visualize it, we should have 2D. So height is this, and this count of the numbers is this, and let's suppose histogram, it'll show like this. But now in terms of, let's suppose you want you have the earth, you have the whole earth. So how is whole earth divided in terms of its places? We have latitude and longitude. Okay, and based on this latitude, longitude, you have temperature. Now here these two are my independent variables, and this is my dependent variable, because based on latitude, longitude, the value temperature is given a particular value, assigned a value. Let's suppose if you are from Kashmir, you have latitude, you have a longitude, and corresponding to that you will have, let's suppose this is talking about average temperature, some average temperature of that place. Now you see that based on this latitude, longitude, you have two independent variables, and now dependent variable is one. Now it makes the job difficult. What we are saying is we must have a 4D system. We must have 4D coordinate system. Why? In order to show you this, at least not 4D, sorry, at least we should have 3D system. So 3D will be something like this. So this is latitude and this is longitude. Okay, and then let's suppose this is temperature. Okay, and then if this is the point, but it is quite difficult. If you want to bring this into 2D, what you can do is you can see, okay, let's have latitude longitude only, let's have latitude and longitude, but now I'll color these things differently. Okay, I'll color it based on certain color bar. So I have a color bar over here which I'm saying 0, let's suppose this white color basically means temperature between 0 to 10 range. So 10 to 20, this is the color, let's suppose some color range over here, and I'll color the points accordingly, something like this. Now you can see that I captured three-dimensional data. The data actually was, I had two independent variables and one dependent variable. Now this dependent variable is computed by these independent variables. So if I can have this latitude, longitude, and this temperature, this can be shown by a color. If this can be shown by a color, it cannot be just a color. So in heat map, it is shown as a color, but it can be also in the size. So we saw in the scatter plot. In the scatter plot, we also saw that. So based on the frequency, we showed the color. So we are basically showing the size there. So if you can somehow make sense the data like this, so that's why you actually require 3D coordinate system. You need three coordinates. You have two independent axes and one dependent axis. And but here what you can see in the 2D, you are just bringing the data down to 2D and making sense out of it. I hope this answered the question. So now if you see, we'll go to the what is called as contour plots. Seeing the exact spelling that I don't miss it. So what are these contour plots now? So in this, again the same problem that I just discussed. If you have three things, if you have x, y and z, if you have sort of these three things now, okay, and you want to show these values, let's suppose you have a function which is not just parabola, which is, let's suppose, a paraboloid, which is in 3D, x, y, it has x, y and z axis. So now you can see that these x, y and z, these can be, let's suppose, 4 variables or something like that. It can be x, y, z, and then they give you some certain value. Okay, these x, y, z, and they have a certain value associated with that. Or maybe the problem that we just solved, we have x, y, and it gives z, something like this. So what these contour plots basically are, they display a 3D surface, okay, on 2D plane. By showing the lines, they actually connect the things which are at the same height. Okay, I'll give you a physical example. If you see mountain, let's suppose consider this as a mountain. Mountain is like this, consider it in 3D. Okay, and now if you see height of the mountain, height. So now you can see, if I just draw a ring around this, draw a ring some of this sort. So all the points on that ring will have the same height. Who agrees on this point? All the points on that ring will have the same height. Okay. Now what you can do is, if I have this height and you have this height of the mountain. Okay, this is the thing capturing height, and now you have this mountain over here. So in here you might have this. If I show you a 3D object for it, if I have something like this over here, let's suppose this is a mountain. Consider this as a mountain. Okay, now this mountain is sitting, let's suppose, on the earth. Now you can see, let's suppose this is my x and this is my y. So because it has got length and width, now it has height also. Okay, so what I'm saying is, I have a lot of points which have the similar height. Okay, you can see that it forms a ring. It forms a ring like thing. This is height. Okay, and again, if I have this is the height. Okay, so what can I do is, if I have a 3D object and I want to now project it onto 2D, I can just form these rings. I can say these sort of rings. Let's suppose this is the ring. Okay, or maybe this is roughly the ring. And these things are called as contours. Okay, so what are these contours? Contours basically are these maybe lines or something which connect the points which have equal value. They have equal value. As I gave an example of mountain. So mountain has its length and its width, let's suppose, and then height. So I am saying, based on that, there are different points on the terrain which I call terrain. So they'll have the similar value of the height. So if I just drop these rings around, okay, if I have these circular things and I just project these rings onto the 2D, okay, rings will look something like this. I'll have a ring like this, then a bigger ring like this, rings like this. I'll have a lot more rings like this. So let's suppose, and now what I can do is, if I project them onto 2D, so how will they look like? So these rings will look like this. If you see, so they'll look concentric like this. Okay, this is, if you see it, if you just slice them, if you have a mountain and you slice these rings, you slice infinite rings, then each of them will be a circle roughly. If this mountain looks like, let's suppose, a conical shape or something. Okay, but usually it's not conical, and then you can see roughly it looks like some curved surface, closed curved surface. But what if I project them? Okay, so what if I project them? Do you agree that it will look like this? How many of you agree that it will look like this? It will look like this one. So if I have the mountain like this, I am slicing the rings out of that, and then these rings will look like this. All these rings, what they signify? Each ring, the points on that ring have the same height. Okay, and these things are called as contours. Okay, and now this 3D thing has been made into 2D. That's why I'm saying this contour, it displays a 3D surface onto a 2D plane by showing the lines that connect the points to the equal value. Okay, it shows the lines, and these lines are the points which are having equal value. Okay, and these lines are known as contours. Okay, and they represent, let's suppose you have this x and y, you have x and you have y, and then you have this z. Okay, now this z is shown by the contour lines. Okay, and this is used in optimization a lot. We'll use a lot of this in optimization. Okay, how will these contours look like? I'll show you how these contours look like. Let's go to the code. I hope that contours are clear. So can I assume that you are clear with what contours are?
Yes, sir. Very well explained.
Nice. So let's now go to the code. So if I see this, so if you see this snippet of code, so I am generating some 100 x numbers, 100 y numbers, and then I'm continuously using that Gaussian function. So I'm saying np the square root of the sign, and I'm using that, and I'm showing these are the z values. Okay, now what I'm doing is I'm showing contour plot. So how to plot this contour plot is give the x value, give the y value, and based on this x and y you will get a z value, because you can see this x and y are independent values, and this z is a dependent value because it's getting its value from x and y. Now there are a lot of points which will have the same values of z. So now I'm assuming this level 15. I'm saying 15 levels of this, and you will see these contours. Okay, if I'm just plotting it, you can see these contours, and this is the z value. This is the x axis, y axis, and these are the z values. So, and there's a color coded also. Let's suppose 0.9 z value is of this color, and it looks a bit his. You have to add good color maps. Okay, so as to get it better looking, so that you can differentiate. You can see this 0.9 values of this. Okay, just think these if this is height. So if the circle is over here, this height is more. So inside, like if you're in the middle, the height is more. If it's a mountain, okay, if it's a mountain of a thing, so it's like that. These are the contours. Okay, let me introduce to you a function which is called as Rosenbrock's function. Okay, Rosenbrock's function. I won't explain you what this function. It's a function which, let's suppose if we draw it, so this function will look. I'll show you how this function will look. So it's actually a function that we can plot in 3D. This function will look like this. Okay, this is the function. Usually function is a line which if it is plotted in 2D, but this is the Rosenbrock's function. So what this Rosenbrock's function is the 3D. It has x, y, and it has z. Okay, function has certain values. So function is it has some coefficients. It's squared, and you can see this. Somehow this function is there. So can you see like this function is in 3D? You can see it if it is visible on the screen. Can you confirm? Now what I can do is if I cut thin slices out of this, if I take slices out of this, okay, and I can create contours out of it. So how to do this contour plot out of this? So what I can do is I can say this is my x, y, and z. So if you see this, I have defined one function. So you can clear this. This is the Rosenbrock's function. A minus x whole square plus b, y minus x square whole square. So this is the Rosenbrock's function. Okay, I have given these parameters a and b. They are the parameters, and x and y are the values. So this is my x and this is my y. So in order to compute this z, I am calling this Rosenbrock's function. This is the function. A minus x whole square plus b, and then I have multiplied by y minus x square. So I should write it if for the clarity purpose. Okay, I'll not tell you the application. It has lot many applications. So this is a minus square plus b, and then we have multiplied. This b is a coefficient again. Oops, y minus x square, and then this is the square of this. Okay, something like this. So this is Rosenbrock's function. This a and b are coefficients, and this x and y, they are the independent variables. So if you see it over here, I am giving this x and y, I am computing the Rosenbrock's function. Okay, now in order to plot this, so in order to plot this in 3D, what I did is I plotted this in 3D like this. So here if you see, there's a plot surface is a function which takes x, y, and z. It will plot the whole surface in 3D. So that's what we got. This function is like this. Okay, I will show you easy function. Let's suppose I'll show you paraboloid. So if I just get a paraboloid function, give me a second, I'll get that. I'll get a good function. I can say ax square plus bx plus c, something like this. Ax square, just write it like this, return a multiplied by x square, ax square plus some b multiplied by x plus c, something like this. And I have to give values to this. I don't want to see precedence. The precedence should be right. I'll call c is equal to 1 or something. Okay, this is one paraboloid function. So if I print it, it should print a paraboloid. This is somewhat a plane, but I think did we write something wrong? I don't know. Okay, anyways, but I just wanted to show you one thing. I just wanted to show you if I draw this looking like plane, I don't know why it should look like a paraboloid, because I assume that this should be a paraboloid, ax square plus bx plus c. This is two variables. So anyways, so you have this function, plot function. I'll go back to the Rosenberg's function. That's why I don't like surprises. I should have actually brought the function. So you can see this function is over there. So now this function, basically, if you see this is in the 3D. This is 3D surface. So how to plot the 3D surface is plot surface x, y, and z. And this is how you get it. Now for this function, if you want to get these contours, if this is a function for which you want to get contours, you basically want all the values where it is same. So what you can do is you can just say add contours and levels, so which we have done earlier also. So if you see this contour function, this was the contours that we said contour plot is plt.contour, and that's what we'll do over here. So we'll do the same thing over here. I'll plot these contours. So contours will be some sort of circles, and maybe it can be irregular surfaces also. So this will do a lot in optimization. Okay, so this is our surface. Let's suppose we are taking this figure, and now I'm saying contour plot is x2 of contour, and then x, y, and z levels 30, create 30 levels, and this give the c map. It's x, y, and z. Now it should show me two functions over here. So if you can see, this is the function that's in 3D, and I have converted this same 3D function into 2D by using the contours. Okay, both of these carry the same information. Okay, this is my x and this is my y. Here this is x and this is y. Okay, this is x, this is y, and above thing is z, and this is z over here. So the height is z. And similarly here we have x and we have this y, and the z basically is the function value. So here how is it defined? So you can see by these contours. Okay, and this will be frequently used in optimization. Okay, let's create a 3D paraboloid. I got the equation for paraboloid. So paraboloid equation is x square plus y square. It's not just, this is the paraboloid equation. Till I was explaining you guys. So this is the equation that is for the paraboloid. So what I can do is I can again import these things. Let me just write it. The same things will be there. Okay, so let me write it because it needs writing from scratch. I can't copy it. So import numpy as np, and then import matplotlib dot pyplot as plt. Okay, now what I'll do is I'll define this MPL, because I just want to also create 3D. I'll create, say, MPL toolkits. So this is how to import 3D axis. Okay, and now I'll just create this data. So I'll define a grid first. So I'll say x is equal np dot linspace. Okay, how many values I create? I want to create values from -5 to 5, which I was doing earlier also, and I want to create 100 points of that. And similarly for the y, I'll create this. These are my values for y. So now what I'll do is for z, let's first create a mesh grid. So x comma y, this is np dot mesh grid. Okay, and then I'll give this x comma y. And now what I'll do is I'll create this z axis of paraboloid. So this equation I'll use. Okay, this is the equation of paraboloid, x square plus y square. So I'm giving it without coefficients. Now initially that was a plane, actually ax square. I'll have to see why was there something wrong, or was the mathematics wrong. So now x is equal x square plus y. This is my, and now I'll add the plot. So what I can do is I'll say I'll first have the 3D projection. So I'll create ax comma figure. Oops, ax, I should be writing a better code than this. Figure is equal. So then I'll say this dot sub plt dot figure, plt, oops, am I writing plt dot subplots, and then I'll give it a figure size. Okay, and then I'll give you the figure size. Let's suppose some 10, 12, something like this. Till that it should work. Fine. Fig size. This is with the underscore. Okay. Yes. Good. Good. Then this is a little big, 8 by 6 by 8. Let's keep it 6 by, so it is visible on the display. Okay, yeah, it looks good. So now what I can do is on the first, because I'm saying it, let's create this. I'm saying axis.plot. Let's plot 3D object first. So I think this thing I can copy directly from here so as to make minimal mistakes. So x is equal figure to add subplot. So I'm adding subplots 1 to 1 and projection is 3D. Plot surface xyz, which we earlier did, and I'm saying 3D plot of paraboloid. So if you see this, this is the 3D plot of plot. It should be paraboloid now. Oops. There is something is. I reversed it. It should be figure comma axis. Hopefully, yes. So you can see this paraboloid, but doesn't matter where it happened. We have to adjust it. But now what I can do is I can plot the contours, which I earlier did. So I have to just copy the previous code that we did. And then I'll just have this layout also, so that now if you see this, these are the contours. This picture looks too bad because of this 6 and 8. I'll create 10. Something like this. It should look a little better. So you can see this paraboloid. Now you can cut slices and you can see this. These are the contours, and these things basically represent, both of them represent paraboloid. Okay, this is the paraboloid 3D of plot of paraboloid, and this is the contour plot of the paraboloid, and this is a function. Here the same information is represented by these contours. Why am I showing you? Why am I emphasizing it more? Because many the times in optimization you will have a non-convex function maybe, and then we'll just plot its contours. Okay, and each of the problem in machine learning is somewhat a problem where you are solving a function and you are trying to see the global minima or local. You are trying to find the minima. It might be you're trying to find maxima minima in terms of optimization, but in machine learning usually we try to find the minima, and we have a loss function. Loss function will somewhat look like this, somewhat look like a 3D, 4D, 5D, ND curve, something like this. Okay, if you are lucky, you will have 2D, 3D curve, but usually we will have a loss function which resides in higher dimension, and that you'll have to imagine these functions in higher dimension. Maybe I can show you till 3D, and maybe with these contours I can make it easy if it is a function which is in, let's suppose, only 3 variables. But usually you'll have more features than that. Your optimization function will live in higher dimension, but you should get this picture in the head concrete so that you can also imagine in that dimension. That will be a complex function, and that function you try to come up with these local or maybe global minima values so that you minimize the loss function. So loss function is what you are minimizing in machine learning or deep learning, and loss functions will have things like this. If it is a loss function which contains only 3 variables, it will be easy for us to visualize, but many other times, maybe around 90-95% times, these loss functions will have a lot more values than we can imagine. We can maybe visualize in here. Imagination is not bound, we can imagine, but here I just wanted to show you this so that you can visualize these things. Okay, these are the functions of paraboloid things. So I think we are done with the contours, and I hope that you at least learned these things. So here we can stop the playlist of Matplotlib at least for the plot section. So one thing that is pending is animations. It will take me maybe 30 to 40 minutes to cover those animation, but I hope that you at least learned the basics and now you are ready to read the documentation on your own. And there are a lot of features, and a lot of features. When I'm speaking a lot, that means a lot, because I just covered probably 10-20% of Matplotlib, and it is not humanly possible to cover in a short course all the 100% of the Matplotlib, and it's bad also. If I cover everything, what will you do? So I'll just give you enough which probably you'll use 90% of the times when you are coding yourself, and anything you have to do is you should look for the documentation, and sometimes the things won't be available there. So now there are two approaches to that. The first approach which I said is you can maybe mix and match up things and do the things, and the second thing is do also request for a feature also. So if you found something, just maybe add something in the GitHub, go to their GitHub and say I wanted this but it's not there, I wrote a simple snippet of code, this is how I wanted it. Maybe some other people, because it's open source, some other people will come, they'll see okay this feature is somewhat needed by many people, and they'll try to implement it, and you can also contribute in that way. Okay, these are two approaches, but I'll still heavily rely on the documentation, heavily rely on these things. And I think you are now ready to write the visualization, write mathematics for it, and I hope you will enjoy this. So here I'll stop the recording for today.